Hey guys, if I want to sketch a graph of a function as accurate as possible, what do I need? Well, I might need n behavior, right? So what happens as x goes to plus minus infinite, right? Whether there are horizontal asymptotes, etc. I also may wonder whether I have vertical asymptotes, right? Uh, I may want to know what is the domain, what is the range of the function, etc. Right? What else? Well, I can take the derivative, find the critical points, and investigate local minima, local maxima, right? Also, I can consider derivative and find out where the function increases, decreases, right? Great, but we still need one more ingredient, which is concavity, and then I think we can go ahead and consider curve sketching problems. So our learning objectives are: we will define what is a concavity, we will define what does it mean to have points of inflection, we will see another test called the second derivative test for local extrema. We already saw the first derivative test, and then we will consider sketching the graph. Okay, so what does it mean for a function to be concave on an interval? Here's the definition from the book. So we say that a function is concave up function on an open interval if its derivative is increasing, not function itself, the derivative is increasing. And it's called concave down on an interval if its derivative is decreasing. Okay, so what is the situation? So this is what we mean, right? So here the example of a concave up. So if you look at the slopes, so the slopes are becoming steeper, if you like. So it means the derivative is increasing. And if you look at this here, this is an example of concave down. So if you look at the derivatives, if you sketch the derivatives, again it's now it's decreasing, right? The functions who are concave up also known as convex functions. So a parabola that opening up, that's called concave up. So you can, if you to remember, if you like. And the things functions that look like a parabola that opening down, they're called like a concave down, right? So it's opening up like this, it's concave up. It's like opening down, it's called concave down. Well, how do I check it? So, well, look at the concavity, right? Concave up means the function has an increasing derivative. But what does it mean for a derivative to increase? It means if I take the derivative of the derivative, it must be positive, right? And concave down, its derivative decreasing means if I take the derivative of the derivative, so the second derivative, it must be negative. So that's the second derivative test for concavity, right? If the second derivative positive on an interval, then it's concave up. If it's second derivative negative, then it's concave down. So the second derivative gives us an information whether the function is concave up or concave down, etc. So let's determine when the function 3 plus sine x is concave up and when it's concave down. The graph is given on the right in blue color, but we will assume that we don't know the graph, right? I mean, from the graph, somehow you can sort of see that here I see concave down, here I have concave up, etc. Right? So there is some where pi something changes. Anyway, so what we do, we have to take the second derivative. Well, what is the first derivative? It is cosine of x. If you take the second derivative, it is minus sine of x, right? Okay. Well, what do we know about sine of x? Well, for sine of x, we know it's sine, right? From 0 to pi, this is positive. From pi to 2 pi, it's negative, right? Well, Then for minus sine of x, which is the second derivative, I have the opposite. Here it's minus, here it's plus, right? So which means here I have concave down, here is concave up. So you can say the function is concave down on 0 pi, and it is concave up on pi 2 pi. So we usually give the interval concavity as an open interval, avoiding the endpoints, because at endpoints it's not clear what happens. A related notion is what is called point of inflection. Here's the definition. We call a point, the coordinates c and f of c, a point of inflection if at this point the concavity changes, right? Let's say that on the left it was concave up, then it became concave down, or vice versa. Then we call that point the point of inflection. So at the point of inflection, we may have a second derivative 0, or it may not exist, right? It may not exist. Let's consider cubic polynomial and investigate the concavity and inflection points. Well, what we do, we take the second derivative. So the first derivative is 3x squared minus 6x. The second derivative is 6x minus 6, right? Well, like we find the critical points looking at the zeros of the first derivative, we investigate concavity looking at the zeros of the second derivative. Well, we see that this equation satisfies if x is equal to 1, so which means we have to be careful with x equal to 1. We don't have any restriction, so we assume the domain is from minus infinity to infinite, and we have 1 somewhere, right? Now, if my x is less than 1, what happens to f double prime, which is 6x minus 1? If x is less than 1, x minus 1 becomes negative, right? So this is negative. Here, it's negative. If x is bigger than 1, then the second derivative is positive. So here it's positive, right? So it means from minus infinity to 1, I have a concave down function. From 1 onwards, I have a concave up function, like you see in the picture. So we see that okay, yeah. So we summarize as follows. So concave down on minus infinity to 1, concave up from 1 to infinite, and because at 1 we have the concavity changes, it means the 1 and the f of 1. So what is f of 1? Well, we see from graph it's 0, but it's like 1 minus 3 plus 2 is 0. So 1, 0. This coordinate is point of inflection, right? Inflection point. Let's look at another example where we would like to investigate concavity and would like to find if there are any inflection points. Well, again, we need to look at the second derivative. The first derivative is going to be 1/3 x to the minus 2 over 3, and the second derivative would be minus 2 over 9 x to the minus 5 over 3, right? Or if you like, this is minus 2 divided by 9 cube root of x to the 5. All right. Well, what do we see here? So we see that at x equal to 0, we have a problem. In fact, even derivative doesn't exist at x equal to 0, right? So which means it's an infinite derivative. So which means we have infinite tangent, right? The vertical tangent. So that's the tangent line, vertical tangent. Now, so x equal to 0 looks an important point. So what we do is we look at again the real line from -infinity to infinite, and with attention to 0. Now if x is less than 0, what do you get for second derivative? Well, we have -2 divided by, so the denominator also becomes minus, so this is minus is going to be plus, right? So here it's positive, and if x is positive, then this becomes negative. So which means here I have concave up, there I have concave down. Indeed, from the picture we see that here it's like opening up, here it's like opening down, and because the concavity is changing, we also see that this 0, 0 is again an inflection point. So here it's -infinite to 0, concave up, from 0 to infinite, concave down, right? So concave up, here it's concave down. Second derivative test for local extrema. Let's recall what was the first derivative test. So for the first derivative test, we first find the critical points, right? The points where the derivative is 0, right? So the horizontal slopes. And then if the function is increasing, so first derivative is positive, and then it becomes negative, it means local maxima. And if the derivative is negative and then it becomes positive, it becomes a local minima, right? Well, how about the second derivative test? So second derivative test is, well, as the name says, it's related to the second derivative. Again, let's say that f prime is 0, right? Again, we have horizontal slope at c, but if f double prime is negative, then the f is going to be local maxima, right? Well, what does that mean? The second derivative to be negative, it means my function opening down, right? Here somewhere I have c, horizontal, right? So as you can see, I mean, from picture we get local maxima. Well, how about local minima? Again, if the c is the critical point, plus if the second derivative is positive, it means it's now opening up, right? So it's opening up, and here I have a local extrema. So then this local extrema in fact is going to be local minimum. Okay? If f prime is 0 and f double prime is 0, then test fails. We don't know what happens. Okay? We don't know what happens. So now we are more or less ready for graph sketching. So what is the procedure? First, you may identify the domain of f, and if there are any symmetries, like whether this is an even function, odd function, etc. And then you sort of calculate your first derivative, second derivative, because we know that they give us useful information. And then from the first derivative, you can find the critical points, right, where the derivative is 0 or fails to exist, etc. And then you find out whether these are like local extrema, right, whether minimum, maximum, etc. And then what else? Again, from first derivative, we can find out whether the function, where function is increasing and where it is decreasing, and then we start investigating the points of inflection and the concavity, right, where it's concave down, where it's concave up, etc. You furthermore identify whether you have asymptotes, right, like horizontal asymptotes, vertical asymptotes, etc., so on and so forth. And further, what you can do, you can investigate the intercept, right, some important key points that we found in all these sections, plus intercepts, etc. And finally, with all this information, you carefully sketch the curve. So we will do one example. Okay, so let's try to sketch the following graph: x plus 1 squared divided by 1 plus x squared. We can first start finding intercepts. X-intercept. X-intercept means what? When does this graph intersect x? It means you set y equal to 0, right? So you set y equal to 0 means x is -1, right? At -1, we get y0. Well, what is y-intercept? Y-intercept is easier. It simply means you let x equal to 0. If you let x equal to 0, we see y equal to 1. So my graph has to pass x equal to -1 and y equal to 1. Okay, now what was the procedure? First, we want to find the domain. We do not have any problems like division by 0, so it means the domain is from -infinite to infinite. We do not have any symmetry. It's not even function, it's not odd function, etc. Okay, what next? Next we find derivatives, right? Let's take the first derivative, apply the quotient rule. We have 2x plus 1 times 1 plus x squared minus x plus 1 squared times 2x divided by 1 plus x squared squared. So after simplification it becomes 1 minus x squared divided by 1 plus x squared squared. Now we find the second derivative. Again, apply the quotient rule. We get minus 4x 1 plus x squared squared minus 2 1 minus x squared multiplied by 2 1 plus x squared times 2x, everything divided by 1 plus x squared to the power 4. After simplification, it becomes 4x x squared minus 3 divided by 1 plus x squared cube. What next? Next comes to investigating local extrema, right? Well, let's find the critical points. Critical points, we set this equal to 0, and this implies that x is plus minus 1. So these are my critical points, right? Great. So at the critical points, if x equal to -1, let's apply the second derivative test. So we look at the second derivative, evaluate second at -1. So we see minus 4 times 1 minus 3 divided by 2 cubed. So negative, negative, this is positive. So it's opening up. Opening up means this is local minima point, right? And at x equal to 1, the second derivative, it's 4 times 1 minus 3 divided by 2 cubed. Now this is negative, so this is opening down, which means I have a peak, right? So this is going to be a local maxima. So fourth, we would like to investigate monotonicity, right? Where the function is increasing, where it's decreasing. Again, it's about f prime. So you plot on real line your critical points, -1 and 1. So if your x is less than -1, what happens to the f prime? If it's less than -1, this 1 minus x squared, it becomes, so x squared becomes bigger than 1, so it becomes negative. So here it's negative. Between -1 and 1, for example, you can plug in x equal to 0. If you plug in x equal to 0, you get positive. And then if x is bigger than 1, then 1 minus x squared becomes negative. Denominator is always positive, so this is going to be negative, which means my function from -infinity to -1, it decreases, then it increases, and then it again decreases. Okay. Okay, what is the fifth step? Well, fifth step is to investigate concavity and points of inflection, right? So which means we set the second derivative equal to 0, which gives us x equal to 0 and x equal to plus minus radical 3, right? So these are the sort of candidates for inflection points. Again, we sketch the real line, plot this points and see the behavior of f double prime. So if you're less than minus square root of 3, it becomes x squared minus 3 becomes positive, x is negative. The denominator is always positive, so I don't have to worry about denominator. The numerator decides the sign, so I see negative times positive, so this is negative, right? So here it's negative, right? It's less than 0, so which means I have concave down in here. And then between square root of 3 and 0. So my function is still 0, so x is negative, but x squared minus 3 is negative 2, so it makes it negative positive, right? So there, so this is from minus infinity to minus radical 3. So then here I have a positive, so from minus radical 3 to 0. So here's concave up, and then what happens between 0 and square root of 3. So if it's bigger than 0 means x is positive, but x squared is still less than 3, so it's negative, so this becomes negative, right? So here I get concave down, and then you can see that we have concave up between square root of 3 onwards. Okay, what else? Well, we see that concavity changes at these points, right? So we can, so the points of inflection, so all three are inflection points. So we say, so inflection points are you need to plug in x equal to minus 3 here. So this is minus minus square root of 3. If you plug in minus square root of 3, it becomes square root of minus square root of 3 plus 1 squared divided by 3 plus 1, 4. Yeah, whatever that point. At 0, okay, so at 0, this is simply 1. And at square root of 3, I get square root of 3 plus 1 squared divided by 4. So these are my inflection. So what is number 6? Number 6 is about asymptotes. So how do we find asymptotes? Well, we do not have vertical asymptotes because denominator is never 0, so no vertical asymptotes. How about horizontal asymptotes? We need to look at what happens as x goes to plus minus infinite, right? So you let x go to plus infinite of this function itself, right? No derivative, no second derivative, etc. X squared. So what do we see? Well, you can apply L'Hopital if you like, or we see that this is like x squared plus 2x plus 1 divided by 1 plus x squared. So you can divide everything by x squared if you like. It becomes like a limit 1 over plus 2 over x, 1 over x squared divided by 1 over x squared plus 1, right? So what we see is and then we get 1. So that's the horizontal asymptote, right? And you can also look at what happens at negative infinite. Again, you can see that it goes to 1. So again, when x goes to negative infinite, we again approach to horizontal asymptote. So now let's try to put all the information together. So I have important points: minus square root of 3, minus 1, 0, 1, and square root of 3, where the function changes the. So from monotonicity, we know that the function is here it's decreasing, then it's decreasing, then it increases, decreases. As for the concavity, here I have concave down, then it's concave up, concave up, concave down, and concave up. So finally, let's try to sketch the graph, plotting all these important points. Zero, 1, square root of 3. Right. So intercept, we know that graph needs to intersect x minus 1 and y at point 1, right? So these are my intercept. So we know that minus 1 is local minima, right? So at x equal to minus 1, what is the function? The function is, well, we know that it's intersects, right? So function is 0. So at x equal to 1, what is the function? It's 1 plus 1 square, 1 plus 1 squared. So this is 4 divided by, so this is 2, right? So 1, 2. Here's my 1, here is 2. So this is going to be my local maxima. So one last thing is I have horizontal asymptote, right? So I have horizontal asymptote. Let's at y equal to 1. So as x goes to plus minus infinite, my function has to approach to this horizontal. So at y equal to 1, I have horizontal asymptote. Now let's try to sketch the graph. So between minus infinite and minus square root of 3, I need to sketch a function that's concave down, and it needs to decrease, right? So it needs to decrease. So it should be a decreasing function, and it should continue until 1, right? Until minus 1, it should continue decreasing. But somehow here the concavity changes, right? This inflection point, and this orange one is my horizontal, so asymptote, so it has to approach. So I need to somehow concave down function, but it also needs to decrease, right? So it's coming from this line, sort of. It's concave down, right? Concave down and decreases. And then between minus square root of 3 and minus 1, it's still decreasing but concave up. Now it's like opening up, but it's still decreasing, right? So it still decreases. It decreases, but, and here it touches here, right? But it's concave up, right? It's concave, convex. What next? Between minus 1 and 0, this is concave up. Again, I need to keep sketching concave up. And now it increases, right? It increases, and it needs to touch this one, right? It does. So that's sort of easy, not so hard. Then what? Between 0 and 1, it still increases, but concave becomes concave down. So this is inflection point, right? So here is concave down. And we know that this is local maxima, right? In fact, it looks like local global. But anyway, so that's the graph. What next? Between 1 and the radical 3, this is concave down, and it's decreasing, right? So concave down and it's decreasing. In fact, we see that from 1 to infinite, it is decreasing, right? So from here onwards, it decreases, but it needs to approach here. So I don't want to pass it, right? So concave down and decreasing. So until here, I have concave down and decreasing, something like this, right? But then it still keeps decreasing, but it needs to concave up. Now it's, so concavity changed, but still decreasing. Okay, so this is more or less the graph of this